Hey guys, welcome to today's class. Have fun.
Welcome to class today. So in the last class on chemistry, we looked at the topic periodic table, periodicity and families of elements. In the last class, we were only able to discuss on the electronic configuration, blocks, S block to F block. And we were able to look at some little properties. But today we'll be continuing the class, like I said earlier from the last class. So we'll be looking at the periodicity of elements now in the periodic table, and also atomic properties, and we'll be looking at some families of elements in the periodic table. So today we'll be going broader into the periodic table. So recap from the last class, I was able to tell us that we have various energy levels. We have the K shell, we have the L shell, we have the M shell and the N shell. I was able to tell us we have different stages of energy level in an atom. So this is the K shell, the L shell, the M shell, and the N shell. So these are the energy levels. This is energy level 1 to 4. And I was able to discuss the maximum number of electrons which these energy levels can carry as 2n squared. So this gives us 2 to 8, 18 to 32, and so on. So quickly now we'll be looking at groups. Groups, what do we mean by group in a periodic table? When we're talking about groups in a periodic table, we are talking about the vertical columns of elements numbered from 0 to 7. These are the vertical column of the elements in the periodic table. And when we are talking about groups now, you have a typical periodic table, something like this. And the vertical columns, these are the vertical columns. I'll be showing us a periodic table, but I just want to analyze simply first. So these are the vertical columns, the ones which are running downwards from top to bottom. They contain elements and they are numbered from 0 to 7. So meaning we have 8 groups in the periodic table, 8 main groups in the periodic table. So we have from group 1, we have from group 1, group 2, group 3, down to group 8, then we have group 0. Okay, I'll be explaining when we get to the families of elements, we'll be looking at the elements in these groups further. So when we're talking about a group now, the elements in a group, they have the same valence electron. That makes the number of the group. So when you're talking about elements in group 1, we are simply saying all the elements in group 1 have one valence electron in the outermost shell. So if, for example, an element X now is in group 1, what that simply means that element X has one valence electron. If an element Y now is in group 3, means that element Y has 3 valence electrons. If an element is in group 7, Z, this means an element has 7 valence electrons, whereas an element which is in group 0, it has 0 valence electrons. So quickly we'll be looking at periods also. When we're talking about periods now, okay, I've said the vertical columns are the groups. Now for the periods now, the horizontal rows are what we refer to as the periods. Now the periods are also numbered. So we have periods from number 1 to 7 in the periodic table also. So you can have period 1, period 2, period 3, down to period 7, also in the periodic table. So what is the simple difference between the period and the group in this case? In the period now, they have the same number of electron shells. These are two different things. In a group now, they have same valence electron, I explained earlier. But for a period now, the numbering shows the number of shells. So for an element in period 1, it means it has one shell number. So if I take an example now, I take aluminium for example. Aluminium, now if you are checking the periodic table, and this is a periodic table, I'll be showing it in bits as we go on. I'm sure we are familiarized with the periodic table. Now this is aluminium here. Aluminium is in 1, 2, 3. Aluminium is in period 3. And what's group number? It is in group 3. Counting it from the left hand side of the periodic table, which I'll be showing us. So we have 2 other columns. Then we have 3, 4, 5, 6, 7, 8. So aluminium is a member of group 3 and also a member of period 3. So in this case now, what this tells us is simple, that aluminium has 3 valence electrons and aluminium has 3 shell numbers. So aluminium has 3 valence electrons because it is in group 3 and 3 shell numbers because it's in period 3. So writing the configuration now for aluminium will simply be, since it is in period 3, we have 3 shells, and because it is in group 3, automatically it has 3 outer electrons. So that's what the essence of the periodic table is all about. You can figure out various properties of the elements. So we have groups 1 to 8, or you say group 0, 1 because of the valence electrons. So an element in group 8 has 0 valence electron. So group 8 is also known as group 0. So also we have from periods 1 to 7. So from period 1 to 7, that is from 1 number of shell to 7 number of electron shells. So also we're looking at blocks now as related to the periodic table. In the last class, I was able to explain how to configure atoms, electrons of atoms into configurations, an electronic configuration. Now with respect to the periodic table, we have 4 blocks also in the periodic table. And we are talking about the S block. Now we are talking about elements in group 1 and group 2. These form the S block elements. So every element of the periodic table in group 1 and group 2 are referred to as the S block. Now the simple reason why they are referred to as the S block is because of, in their electronic configuration, you remember the Aufbau's principle. You have L1S, 2S, 2P, etc. So for group 1 and group 2, they only have S block electrons. They only have S block electrons for every element in group 1 and group 2. So every of their outermost shell has either 1 or 2 electrons. And this 1 or 2 electrons falls under the S block. So that's why group 1 and group 2 are the S block. So group 1 is also known as the alkali earths. Group 2 is also known as the alkaline earths. So we also have the P block. In the P block now, we have elements in group 3 to group 0. Group 0 is also group 8. So elements from group 3, this is from group 3, 4, 5, 6, 7, and to group 8 or 0. They are all referred to as the P block elements. The P block elements in the sense that also during their electronic configuration, 3p and so on, their outermost electrons occupy the P block elements. Now if you recall that the P block can take a maximum of 6 electrons. So in their configuration, you might have something like P2, can have something like P3, P4, P5, and so on and so forth. So for elements in group 3 to 0, they are referred to as P block elements because in their outermost shells, the electrons are configured to be in the P block. So we also have the D block elements. In the D block elements, we refer to these as transition metals. So these are metals between group 2 and group 3 of the periodic table. So we have the periodic table to be something like this. This for hydrogen, this for helium, then the rest come under. So the space in between, this space in between the periodic table is what we refer to as the D block of elements. I'll be showing us the periodic table. It's what we refer to as the D block of elements. So every element in this area of the periodic table, they have electrons configured in the D block. That is, the valence electrons are usually in the D block. So you also have, so for the D block now, okay, we have transition. Then we also have lastly the F block. So in the F block now, the families of elements in the F block are referred to as lanthanides and actinides, between group 2 and group 3 also, but these are in period 6 and 7. So in the periodic table, you have the D block here. You also have an extension of the periodic table. So these ones are the F block elements, because in addition to S, P, D, F, they also have electrons in their S. In summary of this, what I'm trying to say is that for the S block elements, they have S block electrons. For P block elements, they have S and P block of electrons in their configuration. For D block elements, they have S, they have P, and they have D in their configuration. So lastly, for F block elements also, they have S in their configuration, P, D, and lastly F. So that's what the blocks of elements talks about. So quickly, we'll be looking at a typical periodic table to note the various blocks of the periodic table. Okay, so I want us to closely look at a periodic table. So the reference material I'm using is New School Chemistry. So these are groups of the periodic table. The vertical columns are the groups, while the horizontal rows are the periods. So now I have group 1, group 2. I have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But since this, in most cases now, we refer to this group of elements as the D block. So in this case now, instead of saying 1, 2, 3, we simply ignore this and say group 1, group 2, group 3, group 4, 5, 6, 7, and group 8, or the group 0. So every element now in this group 1, they have one electron in the outermost shell. Every element in group 2, from beryllium down to radium, they have 2 electrons in the outermost shell. Now every element in group 3, they have 3 elements in the outermost shell, same as group 4, group 5, group 6, group 7, down to group 8. Now for the periods now, we have period 1, period 2, we have period 3, period 4, period 5, period 6, period 7. So for each period now, the period signifies the number of electron shells. So for every element in period 1, they have just 1 electron shell. Every element in period 2, 2 electron shells, 3 electron shells. So across the period now, every element here has 3 electron shells. Also across this like this, every element here has 5 electron shells. Across they have 6, across they have 7. So this group of elements here, between group 2 and group 3, is what we refer to as the D block elements. These 2 block of elements here are what we refer to as the S block elements. These are the D block elements, and this an outer section of the periodic table. These are the F block elements. And lastly, every element from group 3 to 8. So this block of elements are what we refer to as the P block elements. Okay. So quickly, we'll be looking at these elements now, which are extracted from the periodic table. I want us to find the period of the element and the group of these elements. Now I've written out the electronic configuration. I am sure you understand how I went about it using Aufbau's principle. Now this is magnesium. Magnesium is an element in the periodic table with atomic number of 12. That's an atomic number of 12. So this is its electronic configuration: 2, 4, 10, 12. So this is it. Now you can see the highest number here is 2. So that is the energy level of the shell. So magnesium has energy level. It has energy level of 2. The energy level is 2, which means this is the number of electron shells. That is, it has 2 electron shells. Now 2, 4, 6, 8, 2, 4, 10, 12. Sorry. So now it has 2 electrons in its outermost shell. 2 electrons in the outermost shell, and it is in S block. So in this case, it also has 2 electrons. So the highest energy level here is 2. That is 2. That is the number of electron shells, while the valence electron is 2. So it is in group 2. And recall that I said group 1 and group 2 are S block elements. It also has S block here. So this is for magnesium. Now for argon also, argon has an atomic number of 18. And this is electronic configuration. So the highest number, you have 1, 2, 3. The highest number here is 3. So it has 3 energy levels, meaning it has 3 number of shells. This is in period 3. And it has 6 electrons in its outermost shell. 6 electrons in the outermost shell. But next to it now is S2. So the S is complete. So that makes it 8. It has 8 electrons in its outermost shell. 3s2 and 3p6. So meaning it is in group 8 and it is a p block element. Okay, now I have chromium. Now chromium is atomic number 24. So for chromium now, you can see the numbers. I have 1, 2, I have 3, I have 4. So for chromium now, I have number 4. The energy level is 4. So meaning it is in period 4. And the outermost electron here has D4. These two are not synonymous. This is 4 to 3. So it has D4. It has 4 electrons in its outermost. Okay, it has D4 and it has S2. Sorry. S before the D. It has 6. Okay, let's say 4 and let's keep 6 now to find the group. I don't know the group yet. So, and I also have the blocks here. I have S, P, and D. So it is a D block element. So what's part of the periodic table will I find it? Since it is in period 4 and the group, because of the D block elements now, it is not going to be a group 1 element, a group 2 element, group 3 or anything. It is going to be in the D block element. That is the transition element. So chromium is a transition element. So lastly, I have uranium, very large atom. This is the electronic configuration. I have 1, 2, 3 up till number 7. So uranium is in period number 7. This is in period number 7, and for the group, which I don't know, I have 4 electrons here. I have S before it. I have 5. I have 7. So I don't really know the group, but because I know the outermost electron has F electrons filled, this is an F block element. So for an F block element, if I want to find it in the periodic table, I simply go to either the lanthanide or the actinide series. So to locate these electrons now, you have used the period and groups. So this is a group 2 element. This is a group 8 or group 0 element. This is a D block element, transition element, and this is an F block element in the lanthanide or actinide series. Okay, so next up now we'll be looking at atomic properties. Atomic properties. So you have various atomic properties in the periodic table. We have majorly five major properties. So I was able to explain in the last class about periodicity. And I said periodicity is the trend or change or variation in the elements as you move from one group to another group, as you move from one period to another group. What are the trends you notice in the periodic table? So this is what atomic properties tells us. So first I have the atomic radius. Now every element has atoms. So each one of them have their various atomic radius. So I have a group of various elements in the periodic table. Each one of them have their different properties. So how does this property relate to one another? Brings us to atomic properties. So the atomic radius now is 1/2 the distance of closest approach between the nuclei of atoms in the elemental substance. We'll be able to establish what an atom is. This is an atom of an element now. Now it is very difficult in most cases to just figure out the radius of this atom, because an atom now has electrons, and these electrons are constantly in orbits around the nucleus. Now because these electrons are constantly in orbits around the nucleus, it will be very hard to predict the radius of this atom. So that's why the definition of atomic radius came as a discovery that the atomic radius is 1/2 the distance of closest approach between the nuclei of atoms in the elemental substance. Now using this, they used the iodine elements as a simple basis now. And for iodine, you have one atom of iodine and another atom of iodine that are close together, center of the atom. Now the total distance from here to this point is the total distance of this iodine atom. Now half of this distance is what we refer to as the atomic radius, which is the distance from here to here. So in other words, we can say atomic radius is 1/2 the distance of closest approach between atoms which are covalently bonded. So that's what we simply refer to as atomic radius. So for various atoms of elements in the periodic table, they have their various atomic radius. Every element has their various atomic radius, and this atomic size now tends to differentiate from one another. So as you are moving from the left to right of the periodic table, and you are moving from top to bottom of a group, now how does this atomic radius or atomic size changes? So from moving left to right now in the periodic table, you have, let's say, 2, 3, 4, 5, 6, 7. These are elements. 2 electrons, 3 electrons, up to 7 electrons. They have their various atomic sizes. So from when you are moving from left to right of a periodic table, the atomic radius tends to decrease. So moving left to right now, the atomic radius decreases from left to right, while when you are moving downwards the periodic table, the atomic radius increases. Now this is group 1 elements, hydrogen, lithium, downwards, and these are members of a particular group now, a particular period rather. So these are let's say it's a period 2 elements now. So as I move from left to right, because there is just an increase in the there's just an increase in electron of 1. The increase in electron is just one increase in electron. So this does not really have effect on the size of the atom. So an atom for 2 now, which was like this, now moving left to right, it became 1, 2, 3. So this does not really have any effect on the size of the atom, because as electrons are being added, the nucleus also exerts charge, because the nucleus is positively charged, this electron are negatively charged. So as electrons are being added, protons are being added, and there is a balance of charge. So moving from left to right, the atomic radius decreases, does not increase. While when you are moving from top to bottom of a group, the atomic radius increases, because in this case now, an atom having one shell, when you move to the next group, it has 2 shells. The electron size, the atomic size becomes bigger, so leading to higher or larger atomic radius. So the same thing can be noticed for ionic radius now. An atom does not have charge, does not carry electric charge, whether it's positive or negative. For the ionic, for an ion now, we have positive or negative charge, which are cations or anions. So this is an atom of hydrogen, and this is an ion of hydrogen now. Now for ions now, the trend is similar to the atomic radius. When you move from left to right of the periodic table, the ionic radius decreases, and when you move from top to bottom, the ionic radius also increases. But since we know for an atom now, A minus and A plus, and when you have an ion, A minus now, this means it's gained 1 electron to become a negative charge. This means that it's lost 1 electron to have a positive charge. So if an atom of an element loses an electron to have a positive charge, the ionic size will definitely decrease. Whereas if an atom gains an electron to have a negative charge, the atomic size increases. So what this simply implies now is that the ionic radius of positive ions are smaller than this atom, while for the negative ions, these are larger than the neutral atom. So that's what ionic radius is all about. I'll move to ionization energy. Now, ionization energy is simply the amount of energy required to remove 1 electron from each atom in a mole of gas, producing 1 mole of gaseous ions. You can read this out. And the key point here is to remove electron, the energy required to remove electron from each atom in a mole to produce 1 mole of gaseous ion with a positive charge. When you're talking about ionization energy, you're talking about the loss or gain of electrons. In this case now, the amount of energy an atom will require to remove 1 electron from, they are talking in simple terms now. This is an atom of hydrogen, and this is an atom of helium. So if these 2 elements wants to combine now, the energy required now, because helium is complete, is in an octet state, we have hydrogen now. So for these 2 elements to combine, this has to donate 1 electron to hydrogen to complete the shell. So meaning they will have to share their electrons together. So the amount of energy required for hydrogen to steal 1 electron now from helium is what we refer to as ionization energy. So ionization energy is the amount of energy required to remove 1 electron from each atom in a molecule to form a positive charge. Like I said now, when an atom loses an electron, it becomes a positive charge. So if helium in this case loses this electron, helium becomes He plus because it has lost this electron, and hydrogen becomes H minus. And this is also an illustration actually. So what this means is that this has lost this electron, and so the energy required for hydrogen to pull one electron to itself is what we refer to as the ionization energy. Now moving from left to right now of the periodic table, I'm moving from top to bottom. How does the ionization energy also trend? So moving to right now, left to right, the periodic table 2, 3, 4, 5. Moving from top to bottom of a group 1, 3, 11. This is group 1. How does the ionization energy trend? Ionization energy depends on three important factors. Depends on the distance of the outermost electron from the nucleus, depends on the size of the nuclear charge, and the screening effects of inner electrons. I'll be explaining these three very quickly. When you say it depends on the distance of the outermost electron, okay, you have hydrogen now, and you have another element. Let's see, this is another element now with electrons are filled, and let's say this is calcium now, 20 electrons. So this has just one energy level and three energy levels. Now for you to remove one electron from hydrogen atom, you require a very high amount of energy, high ionization energy. Whereas to remove electron from calcium, you require a lower amount of energy because it has 20 electrons. So if it loses one, it is not that effective on the atom. So what this means is that as you move from left to right of a periodic table, the ionization energy increases. As you move from left to right of the periodic table, the ionization energy increases. This is because as you move from left to right, electrons are being added to each orbital. This becomes 3, this becomes 4, this becomes 5. So as you move from left to right, the tendency of these atoms losing electrons become high. So this has 2 now. The tendency for it to lose its 2 is very high. The tendency for this 3 now to lose any of its electrons is also very high. As it moves this way, it's very high. So when you move from left to right of a periodic table, the ionization energy increases. Whereas when you move downwards in the periodic table, the ionization energy decreases. Why does it decrease? When you move from top to bottom of a group, in a group now, you have increasing number of shells. The number of shells increases. So as the number of shells increases, the atom becomes larger. So the atom is the nucleus now. The atom cannot take full care of the outermost electrons because of the high number of electrons, the high charge. So electrons in this point, at this stage, can easily be lost when compared to electrons at this point closer to the nucleus because of the nuclear charges. So when you move down in a group, the ionization energy decreases. The ionization energy decreases because moving down the group now, hydrogen here, the ionization energy you need to steal this electron is very high. As you move downward to 3 number of shells, 4 number of shells, 5 number of shells, the tendency to remove any electron is very easy because increase in number of shells makes electrons to be easily lost because the nucleus cannot effectively carry out its repulsion forces to attract the electron towards itself. Remember that the nucleus is positively charged and the electron is negatively charged. So also the size of I've explained the size of the nuclear charge and the screening effect of inner electrons. Now for very large electrons for very large atoms, I'm using calcium now as a simple illustration, and hydrogen here. Now calcium has 20 electrons, very high number of electrons, various energy levels. This has just one electron and one energy level. So the ionization energy here is lesser compared to the ionization energy here, which I explained initially. This is what we refer to as the screening effect of inner electrons. So because the size is very big, these inner electrons in energy level 1, energy level 2, they are shielding the nucleus from this electron in energy level 3. This is 1, this is 2, this is 3. 1 and 2 are shielding energy level 3. So to steal this electron is very easy. So that's why the ionization energy in most cases for large atoms are usually smaller. So that's why when you move from left to right, the ionization energy is increasing, whereas when you move downwards in a group, because of the increasing number of shells, the ionization energy decreases. Okay, so next we have electron affinity. Electron affinity is the energy released when a gaseous atom gains an electron to form a gaseous negative ion. I explained earlier, when an atom gains an electron, it has a negative charge. But when it loses an electron, it has a positive charge. So I explained using this illustration, if you can remember now. So in this case now, electron affinity is the opposite of the ionization energy. Ionization energy has to do with the energy you use to remove this atom. But in this case now, the energy released when the atom now gains electron is referred to as electron affinity. In this case now, the energy released when this atom loses this electron is the ionization energy. The energy released, the energy used to remove this atom. But in this case, when this atom gains this electron, this is the electron affinity. Is the energy released now when the atom gains electron. So it is an energy used for attracting electrons to atoms. So similarly, the trend now for this in a periodic table, and when you move from left to right of a periodic table, 2, 3, 4, 5. Now what simply happens is that, okay, what happens? Okay, I was trying left to right, talking about left to right now. So moving from left to right of the periodic table, the electron affinity increases. The electron affinity increases because electron affinity talks about the energy released when an atom gains an electron. So moving from left to right of the periodic table, the electron affinity increases because this is as a result of the addition of more electrons to each atom of the elements. Whereas when you are moving downwards from top to bottom, the electron affinity decreases. It tends to decrease. So this is as a result of, for the atomic radius now, an element with a very small atomic radius has a very high electron affinity, whereas an element with a large atomic radius has a low electron affinity. So for a very small atom now, it has higher tendency to be attracting electrons to itself, whereas a large electron has a lesser affinity to attract electrons to itself. So as you move from left to right of the periodic table, the atomic size decreases, causing an increase in the electron affinity, whereas moving down the group, the atomic size increases, causing a lesser energy, lesser affinity for electrons by the atom. So lastly, we're looking at electronegativity. Electronegativity of an atom is the power of the atom to attract electrons. Very simple, just buttresses the point of the the electron affinity. So electron affinity, ionization energy, electronegativity, very simple terms now. Ionization energy is the energy released when an atom loses electron. Electron affinity is the energy released when the atom gains electron. Now, electronegativity is the power of that atom to attract electrons to itself. So, as you move from left to right in a period, and the power of the atom to be attracting electrons to itself increases drastically. Increases, sorry, not drastically in this sense. It increases. So you move from 2, 3, 4, 5. Yes, in this case, you have 1, 3, 11. So as you move from left to right of a periodic table, the electronegativity of the ability to attract electrons, it increases, because as you move from left to right, an atom of 2 electrons now compared to an atom of 3 electrons. Now you can see this has 2 electrons, has 3 electrons. It is attracting electrons to itself. So as you move from left to right, the tendency of atoms to be able to attract electrons to form the octet state. So as you move from left to right, atoms tend to form the octet state, which leads to an increase in electronegativity. Whereas when you move from top to bottom of a periodic table, the electronegativity decreases, because instead of atoms to be being added systematically, in that case it is shells. There is an increase in shell level of the atoms. So in summary now, you have families of elements. You have elements of group 1, you have sodium and potassium in group 1. You have group 2, you have calcium, you have magnesium. You have group 3, you have aluminium, the aluminium family. You have group 4, carbon, silicon. Group 5, you have nitrogen and phosphorus. Group 6, oxygen, silicon, sulfur. You have group 7, the halogens, fluorine, chlorine. And you have group 8, you have group 0, helium, neon. So these are referred to as the noble gases. So these families of elements, they have various properties that tend to affect them. So the families of elements is as a result of the similar characteristics of these elements. So elements in group 1 now, they have similar characteristics, such as they have a valency of 1, they have a univalent number of 1, because each atom has just one valence electron. So they easily donate their electrons to form various compounds, because they can easily lose this electron. In group 2, you have calcium, magnesium. They belong to group 2. They are divalent because they have 2 valence electrons. 2 valence electrons. They also donate electrons. So that's why these two groups are referred to as alkali and alkaline earth metals. They readily donate their electrons to form the octet state. So as you move further, also you have group 3. They have 3 valence electrons. They also form compounds readily because of the ability to donate 3 of the electrons. But in this case now, the most reactive elements are group 1 and group 2, while the less reactive are group 7 and group 0, because they already have almost an octet state, so they are less reactive. You have group 5 also, you have nitrogen, they have similar properties also. They have valences of 5, some have valences of 3. You have group 6, you have group 7. Group 7 are the salt formers, they are the halogens. They are the most reactive non-metals. So as you move from left to right of a periodic table, you notice there is a change from metals to non-metals to metalloids. You have the transition elements and so on and so forth. Okay, so as you move from left to right of the periodic table now, so in summary now, looking at the properties which I explained earlier. So the properties. So across the period now, the atomic radius increases. So moving from left to right across this period, the atomic radius increases because as you move from left to right, more electrons are being added, increasing the atomic sizes. So increase in atomic radius from left to right. Whereas when you move down, across the table, the atomic radius decreases. When you move from left to right, it decreases because as you add more electrons, the nucleus attracts them to itself readily. So leading to lesser radius, lesser distance between the electron and the nucleus. Whereas when you move downwards, the atomic radius increases. Moving downwards now a group, the atomic radius increases because of the increase in number of shells. Ionization energy across increases. So moving across the period, the ionization energy increases. Remember, ionization energy is the energy released or the energy required to lose an atom. So the electron affinity, you also have the electron negativity. So these are families of the elements. You have group 1, the alkaline earth metal, the alkali earth metals are the transition elements. These are the lanthanide series, the actinide series. These are the group 3, group 4, group 5, group 7, the halogens to the noble gases. So quickly looking at some examples. This is a past question objective. Number 3 says, which of the following metals react slowly with cold water? The answer here is calcium. It's one of the properties of calcium of group. It's one of the properties of group 2 elements. They react slowly with water. They have 2 electrons in the outermost shell, so they are readily reactive to lose these electrons, combine with water to form basic oxides. In this case now, it's calcium. So we also have another question here. So which of the following elements has the highest ionization energy? We have calcium, chlorine, fluorine, and magnesium. So in this case, we can quickly picture the arrangement of these elements. Now you have the periodic table, something like this. You have chlorine here, you have fluorine, which is on top of chlorine in the periodic table, fluorine, chlorine, calcium, and magnesium. So calcium is on this part of the periodic table. And you have magnesium here. So this group 2, and we have group 7. So and atomic, which has the highest ionization energy rather, and the ionization energy of atoms and of elements in the periodic table increases from left to right. So if it increases from left to right, these have lower ionization energy compared to this. So this is where we have to consider. So and the ionization energy decreases from top to bottom. So meaning fluorine we have an higher ionization energy compared to chlorine. So that's why chlorine we have the ionization energy there. The answer here is fluorine. So here we have calcium and magnesium belong to the same group of periodic table because both are metal, because both are cations, because they both form colorless salts, because they both have number of valence electrons. And the answer is this. They both have the number of valence electrons, they belong to the same group. And you remember that for you to belong in the same group, you must have the same number of valence electrons, whereas for you to belong to the same period, you must have the same number of electron shells. So the answer is this, because they have the same number of valence electrons. So we have another example here. It says the group to which elements belong in the periodic table is determined by the number of what? Electrons, core electrons, valence shells, valence electrons. Valence electrons tells us the group, while the valence shells tells us the period, not the core electrons, not the electrons. So also I have another past question here. Is NECO. Number 5 here. In the periodic table, calcium and magnesium belong to what? Calcium and magnesium. So to analyze this, you have calcium with atomic number 20, and we have magnesium with atomic number of 12. For this now, this has 2 valence electrons, also this has 2 valence electrons. So in this case, whereas they have 2 valence electrons, meaning that they belong to group 2 in the periodic table. So we have, okay, it says elements in group 7, they are known as the halogens. The actinides is at the F block. The alkali metals are in group 2, it's at group 7. These lantanides are in the F block also, while the noble gases are in group 8 or group 0. So the answer here is halogens. So also it says in the periodic table electronegativity dash each of these options. And recall that you move from left to right of the periodic table, the electronegativity increases. Whereas when you move down the periodic table, the electronegativity decreases. So from left to right of the periodic table, electronegativity increases because there is tendency of these atoms to be attracting electrons to themselves to increase to reach an octet state rather. So from left to right, electronegativity increases across the period, remains constant, no. Increases across the period but decreases down the group. So lastly, I have an example here. It's a theory question. It says a metal has electronic configuration this. It asks to name the metal, the period and the group, and also give product of the reaction with cold water. So we have 1, 2, 3. So definitely the highest number of energy level here is 3, 4. Sorry, 3, 1, 2, 3, 4 is the highest energy level. So this belongs to period 4. And number of electrons in its outermost shell. The number of electrons in the outermost shell is 1. So the group is group 1 and this period 4. So the metal, that's 2, 4, 6, 2, 4, 10, 12, 18, 19. That's 19 electrons. So this gives us potassium. And you're asked to find the products which is formed when it reacts with cold water. So you have plus water to give us KOH plus hydrogen gas. So you can balance this equation. To balance it, just put 2 here. Put 2 here also. You put 2 here. Balanced equation. So thanks for listening.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.